Hey guys, chapter 23, Gauss law, question number 12. Okay, question number 12. Figure shows four Gaussian surfaces consisting of identical cylindrical midsections but different end caps. The surfaces are in uniform electric field E that is directed parallel to the central axis of each cylindrical midsection. The end caps have these shapes S1, convex. Okay, so let's first go through the diagram. We have four Gaussian cylinders. Okay, we have four Gaussian cylinders. Each cylinder consists of a midsection which is cylindrical in shape. This midsection, this part is cylindrical in shape. This part is cylindrical in shape. This part is cylindrical in shape, and this part is cylindrical in shape. Then at the two ends of this cylindrical part, this midsection, we have caps put on it of different shapes. In the first case, we have a hemispherical surface, okay, hemispherical surface with convex side lying on the outer side and convex side lying on this side here. So hemispherical surface, hemispherical caps. Then hemispherical caps like this. So hemispherical surface is this way. And we have a hemispherical surface like this here. So it's inverted. Okay, here you have it this way, then you have it here this way, inverted. Then we have a cone here. So this is a cone here. And the same cone here, cone shape. And here we have a flat surface, flat plane. Plane surface above and plane surface below the cylinder. Okay, now. So the end caps have these shapes S1. S1 is the first one. Convex hemispheres, S2 concave hemispheres, S3 cones, and S4 flat discs, okay, flat plane surfaces. Rank the surfaces according to part A, the net electric flux through them, and part B, the electric flux through the top end caps greatest first. Electric field is given. Electric field is pointing this way and is parallel to the central axis of the cylinder. Okay, parallel to central axis of the cylinder. So electric field is this way here. If I draw a few lines, electric field is this way. Again, if I draw lines like this, is this way. Again here, this way. If I draw it here also, some of the field lines like this. So we have to rank them according to the flux through these surfaces, electric flux through these surfaces greatest first. Okay, greatest first. Field is uniform. Okay, uniform electric field. Now, you can clearly see the number of field lines going into this surface is same as number of field lines going out of it. So electric flux through this closed surface is 0. All of them are closed surfaces. The midsection is the cylindrical one, then you have the caps of different shapes. So all of them are closed surfaces. Or we can do it this way. There is no charge enclosed by the surfaces. All of them. There is no charge enclosed by the surfaces. So electric flux according to Gauss law must be 0. Okay, electric flux must be 0. Or you can visualize it this way. The field lines going in is same as the number of field lines coming out. The number of field lines going in is same as number of field lines coming out from the top. The number of field lines going in is same as number of field lines coming out from the top. Same is the case here. Number of lines going in is same as number of lines coming out. So flux in all the cases is 0. Okay, so flux in all cases is equal to 0. So if we have to rank them according to the flux through them, they all tie. Okay, all tie. And all of them are having 0 electric flux through them. Then part B, the electric flux through the top end caps. Just the top end cap. So we don't have to consider all of the surface. Just the top end cap. Just the top end cap which is like this here. Just the top end cap which is a cone here. And just the top end which is a flat surface here. Okay, we have to rank them according to the flux. So let's consider this one first. So if we have a hemispherical surface this way, okay, if we have a hemispherical surface this way, then we have some field lines like this. If we imagine a flat surface here, a disk here. Okay, a disk here. Then the number of feeder lines going in through that disk, through that plane surface, is same as number of feeder lines coming out from the hemispherical surface. So flux through this flat surface, is same as flux through the hemispherical surface. Now, if this flat surface is having radius r, then its area is pi r square. And if electric field is E going through it this way, normally going through it, then flux through the top end is E into pi r square. Okay, E into pi r square. So flux through the hemispherical surface is same as flux through this flat surface, this disk which we have imagined there, which is kind of a cap for this hemispherical surface. Then exactly the same thing we note in the second case. Well, in the second case, we have the same hemispherical surface, but inverted. So it's like this. We have this hemispherical surface like this. And we have some electric field lines. Electric field is going this way. Again, if we imagine a flat disk here, well, the sizes are same, so radius is going to be same. This one, we assume radius to be r. This one will also have the same radius r. Now again, the number of feeder lines going through the hemispherical surface is same as number of feeder lines going through this disk. So flux through the hemispherical surface is same as flux through this disk, which is same as phi is equal to E into pi r square. Exactly same as this one. So flux here through the top is again E into pi r square. Same goes here. We have a cone here. And electric field lines like this. Flux through the flat surface, which we imagine here, flux through this flat surface, this disk which we imagine here, is same as flux through the conical surface. And this flat surface is again pi r square, so flux will be E into pi r square. And this surface is already a flat surface, so flux will be E into pi r square. So flux through top end, okay, top cap, in all the four cases is same. Okay, so part B, again all tie. And flux in all the cases is E into pi r square, where r is this radius here, which is basically radius of the cylinder. Okay, which is basically radius of the cylindrical part. Is that fine? So all of them tie. All of them will have same flux through the caps, top caps, and as per the complete surface is concerned, flux will be equal to 0 because there is no charge enclosure, or flux going in from one side is same as flux coming out from the other side. With the result, total flux is 0 in all the cases. So all tie in part A and all tie in part B as well. Is that fine? Okay.